Good morning, ladies and gentlemen, and welcome to ACTOM's webinar on solid dielectric insulated switchgear, the future of fixed pattern MV switchgear technology. Before we start, I just need to give you a few webinar considerations. Attendees are reminded to ensure the volume is turned up on your device. Ensure you have a stable internet connection. This will ensure the streaming and audio will run smoothly. Attendees can ask questions via the questions panel located within the GoToWebinar control panel. By default, the control panel is located on the right-hand side of your screen. The chat function is reserved for webinar organizers and panelists to communicate with attendees. Attendees will not be able to chat with each other, however, are encouraged to ask questions. A recording of this webinar will be made available on the SAIEE TV channel on YouTube. You will find the registration link in the chat box. Please register, it's free. And this recording will be listed under the SAIEE Corporate Partner playlist. The certificate of attendance will be issued a few days after this webinar. Now, the reason we're here this morning is with over 70 years of experience in medium voltage equipment, ACTOM MV Switchgear is the largest manufacturer and supplier of medium voltage solutions in the Southern Hemisphere. Their offerings include indoor switchgear, outdoor switchgear, containerized solutions, and retrofit options. Additionally, ACTOM MV Switchgear specializes in repairing and maintaining electrical works. All of their products comply with the latest SAIEE and IEC standards, and quality is assured through the ISO accreditation. The comprehensive range of services and products offered by ACTOM MV Switchgear makes it the top choice for both green and brownfield projects. With the most extensive installed base in Africa and a well-established after-service division, they ensure support for all new and legacy products through spare holding and 24/7 availability. ACTOM MV Switchgear aims to exceed client expectations, foster long-term relationships, and guarantee customer satisfaction. I'd like to introduce you now to both our presenters this morning. Red Kelly, who is the Design and Development Manager for ACTOM Medium Voltage Switchgear. He studied electrical engineering at the University of the Witwatersrand and obtained his master's degree with distinction in 1996. In 2012, Red was appointed Technology Development Specialist in ACTOM MV Switchgear, responsible for MV switchgear and prefabricated substation product development. In 2021, he was appointed as the ACTOM MV Switchgear Design and Development Manager, responsible for research and development, engineering, and the tool room. Throughout his career, Red has served on numerous NRS, SABS, and IEC technical committees and working groups related to underground cable systems, equipment, and switchgear. He has also chaired numerous NRS and SAIEE working groups responsible for the development and maintenance of various NRS and SAIEE standards. Red is registered with EXA and is a professional engineer and an SAIEE fellow. Our second presenter is Johan Jordan, the Technology Development Specialist for ACTOM MV Switchgear, and he studied electrical engineering at the University of Pretoria and earned his degree with distinction in 1995. In 2009, he was appointed Technical Manager for SGB Smit Power Matla, then Powertech Transformers in Pretoria West. As a Technical Manager, he was responsible for managing the electrical and mechanical design departments and the high voltage test laboratory. Johan gained first-hand experience in transformer design, 3D CAD modeling, FEM field simulations, and HV transformer testing. Johan served as the SABS MC Chair for TC14 Power Transformers up to 2018. In 2022, Johan left SGB Smit Power Matla and was appointed Technology Development Specialist at ACTOM MV Switchgear, responsible for product development and implementation. Johan is currently registered with EXA as PR-Eng. I hand you now over to Red and Johan.
Thanks very much, Minx. Appreciate the introduction and welcome to all of you. As Minx has already introduced us, I will go straight into the presentation, but I'll be presenting first. It's Red Kelly speaking, and by my side is Johan Jordan, and he will be presenting some of the slides in this webinar. In terms of what we want to cover today, well, Minx has effectively given you a background as to who we are and what we're involved in. Then we're going to look at the different switchgear types, just an overview, and some of the relevant IEC standards, specifically insofar as high voltage switchgear and focusing more onto medium voltage switchgear. We're then going to look at what exactly is SIS and what it is not. Then take a look at some of the SIS assembly architecture, as well as the different options and circuit configurations. Then Johanna is going to take us through some slides on the effects of the technical performance parameters and important issues to consider in the design of solid dielectric insulated switchgear, or SIS. We're going to look at key specification parameters and then briefly cover the relevant issue of the latest EU regulations on fluorinated gases, and specifically SF6, and then hopefully draw some conclusions. And apologies if you hear some background noise, but that's the joys of working in a switchgear manufacturing organization. I hope the sound is clear. So just briefly, for those of you who may not be too familiar with the switchgear, there are various types of switchgear available, and it's important to differentiate between the insulating mediums and the interrupting mediums. Over the years, I've often found people don't easily or differentiate between the two and have a clear understanding of the functions of the different mediums. So in terms of insulating mediums, not that this is necessarily exhaustive, but the most common types are oil, often referred to as oil insulated switchgear, AIS or air insulated switchgear. Then you've got groups of different gases. Predominantly in the market is still SF6, sulfur hexafluoride. There are also now alternative gases and gas mixtures which are being developed and by certain manufacturers as an attempt to reduce or provide alternatives to the SF6 gas due to the global warming potential of SF6. And then there's dry air as well. So that's controlled air, sometimes referred to as synthetic or green air, but it's effectively just air with a controlled amount of humidity. Those collectively would be grouped as GIS or gas insulated switchgear. Probably worth mentioning that it's not always SF6 when you're talking about GIS. And then there's a fourth category, perhaps lesser known, and that's solid dielectric insulated switchgear, or SIS. And an example of the type of dielectric or insulating medium is epoxy resin, but there are others. So that refers to the insulating medium within a switchgear assembly that typically insulates the live primary circuit conductors. Then, of course, you get the interrupting mediums, so related to the switching device of the switchgear, whether it's a circuit breaker, a load break switch, switch disconnector, and so on. And again, you've got oil, often referred to as an OCB or oil circuit breaker, air, SF6 or alternative gases, GCB, gas circuit breaker, of course, vacuum, which is very common and now the dominating interrupting medium within the medium voltage area, and that would often called a VCB. But it's worth mentioning that you also get semiconductor switching devices, SSCBs, more common in low voltage and HVDC applications, and then hybrid, also for HVDC applications, or an HCB, which is a combination of a semiconductor switching device and a conventional mechanical switching device. The first four, so oil, air, SF6, and vacuum, are all regarded as mechanical switching devices. Then in terms of the assembly, just some examples here. On the left, we've got air-insulated switchgear. We didn't cover oil. It's less common these days. The main reason being is that from a safety point of view, it's difficult to classify and test oil-filled switchgear. So we've excluded that from this particular slide. But on the left, we've got AIS insulated switchgear or air insulated switchgear. And again, although the dominant format or architectures of the withdrawable pattern you do also get air-insulated fixed pattern switchgear, as shown in the bottom example. So it's not necessarily always withdrawable. Then in the middle, we've got GIS or gas-insulated switchgear. Examples there would be SF6 with sealed for life gas-filled compartments, sealed pressure systems as defined in IEC with a typical 20, 30 or 40-year lifespan over which no replenishment of gas is required. And then you've got on the right, although it may not be obvious, an example of a solid dielectric switchgear assembly. And we'll clarify now what exactly that entails and what it's about. But from the outside, effectively, it looks like a metal enclosed switchgear assembly. Briefly, just by way of a very high-level overview, this is certainly not exhaustive, but just an overview of the SANS and the IEC high voltage switchgear standards and the structure. We've got on the right-hand side the different IEC standards. So for example, one of the most common would be 62271-1, which covers all the common specifications for AC switchgear and control gear. -5 is about to be published, which covers the common requirements for DC switchgear. A lot of work going on at the moment for high voltage DC switchgear in the relevant IECs 17, 17A and 17C technical committees. Then in the 100 series, you've got switching devices, for example, circuit breakers, disconnectors, commonly called isolators, but the correct term being disconnectors and earthing switches, covered by 102. And then 62271-103 would cover switches, switch disconnectors, sometimes referred to as load break switches, in the medium up to 52 kV. Of course, there's many other types in the 100 series. And then in the 200 series of the 62271 standard, we've got the assemblies, and most of you might be familiar with the -200, which covers metal enclosed switchgear and control gear up to 52 kV, so effectively medium voltage. Then there's another standard, -201, which is very similar, but the title is AC solid insulation enclosed switchgear, as opposed to metal enclosed switchgear, but also covering rated voltages up to 52 kV. And then, for example, there's other standards such as the gas-insulated metal enclosed switchgear for high voltage applications, so above 52 kV. Maybe just worth noting that -200 metal enclosed switchgear can cover all the different types of architecture, including GIS. So there's no dedicated gas-insulated metal enclosed switchgear standard for medium voltage. They're all covered effectively by -200. And then there's some front-end SAN standards, which cover preferred requirements for the South African industry, standards that were previously NRS standards and then were adopted as SAN standards and effectively extended to a broader audience. Examples of that would be SANS 1885, which covers metal enclosed switchgear, so effectively a front-end standard to -200. And then, of course, that refers to some other important standards, such as SANS 876, which covers the insulation requirements for medium voltage conductors and cable terminations. So just briefly, why the need for front-end standards in South Africa, like SANS 1885? Well, firstly, it's important to point out that these are not contrary or in contradiction to the IEC. They are front-end to the IEC standards, and South Africa, being an IEC member country, has adopted the IEC standards without any modifications. However, amongst the users, there are preferences for certain design parameters, classifications, and then there are certain requirements which are unique, not entirely unique, but which are specific to South Africa. For example, the termination of 3-core cables into switchgear, which is still very common in the medium voltage environment. The standard covers metal enclosed switchgear up to 36 kV. Examples of what 1885 would cover would be preferred ratings, including, for example, the control voltages, 110 volt DC, 30 volt DC for mining applications, and so on. Some of the terminology used, for example, bus section breakers versus bus couplers, as well as preferred colors for switchgear assemblies. It covers assembly and device switching device classifications. People may not be aware, but the requirement for racking behind closed doors is not actually a mandatory IEC requirement, it's a recommendation, nor is internal arc classification mandatory. It's a special test, but SANS 1885 effectively makes, or switchgear designed to SANS 1885 requires racking behind closed doors if it's of the withdrawable type, and internal arc classification, and it provides the parameters. And then it goes on to provide other requirements relevant to the industry, such as cable test voltages, requirements for cable terminations and dimensions to ensure that 3-core cables can be terminated without the need for drop-down boxes or trifurcating kits. And then something else which people may not be aware of is the requirement for 20 kV per millimeter creepage distance for air-insulated switchgear. And Johan will talk about some of those technical issues later when he covers some of the details of this presentation. When looking at metal enclosed switchgear, which is effectively covered by SANS 1885, just a very high level summary. You've got fixed or withdrawable pattern, as we've covered already. You've got different compartments within the functional unit, different insulating mediums. You've also got a choice between different partition classes, so that's the dividing barrier between different compartments within the functional unit. That can be either metallic or insulating. Then you've got compartments, and there's two effectively types of compartments: non-accessible compartments as well as accessible compartments, and we'll touch on those later and their relevance when it comes to solid dielectric insulated switchgear. Then there's important concept within medium voltage switchgear assemblies, and that relates to the loss of service continuity, and there's 4 different categories that are covered. We won't go into detail in that, but we'll just mention what's relevant insofar as fixed pattern solid dielectric switchgear is concerned. And then, of course, the access to the different compartments, specifically the accessible compartments, is also covered in the standards, and all these concepts were introduced in the 62271 series. And then, of course, finally, internal arc classification. Okay, so moving on to the details. By now, I'm sure you've realized that SIS stands for solid dielectric insulated switchgear, and the solid dielectric insulation could be epoxy resin, but it could be alternative materials such as EPDM, silicon rubber, and so on. To some degree, we might have already been exposed to some solid dielectric switchgear insofar as the bus bars on some fixed pattern switchgear. Some bus bars are effectively solid dielectric and fully screened, although they are then used in combination with GIS switchgear. Then we've spoken about -200 as well as -201, and the important thing is that as per the title and definition, -200 covers switchgear that is housed in the metal enclosure, and 201 is switchgear that does not necessarily have a metal enclosure, but is effectively insulation enclosed, and we will show some of those examples. It's important to realize that solid dielectric can fit into both categories, and that it doesn't necessarily fall under -201. In fact, it falls well into the -200 metal enclosed switchgear series of standards. The other thing to note is that solid dielectric switchgear incorporates mechanical switching devices, so it does not mean that it uses solid state. A lot of people initially assume when we talk about solid dielectric that it might imply solid state switchgear, and that's not the case. Solid dielectric insulation effectively refers to the insulating medium, not the type of interrupting medium, as covered earlier. So you would typically have an interrupting device, which could be a vacuum circuit breaker, a vacuum switch disconnector, or a load break switch, is commonly used in the US terminology, as well as a 3-position disconnector, all embedded in epoxy resin, and then, as we'll talk about later, covered by an earthed conductive screen. So the other key aspect to to consider and talk about when it comes to SAIEE switchgear is whether or not it is unscreened. In other words, it's just embedded in epoxy or solid dielectric insulating medium, or whether it has a fully earth-screened conductive layer on the outer surface. And we'll go into details about the impact of the two different designs. The other point to mention is that effectively it's not a new technology. This is not something that suddenly appeared. However, what we've seen in the industry is there's been some drivers, for example, the drive to move away from SF6 and other fluorinated gases to more to environmentally friendly insulating mediums. So that's been a driver, but also developments in the solid dielectric technology has really started to push the boundaries in terms of the ratings that can be achieved, both in terms of voltage as well as current. Today, most solid dielectric switchgear has been limited to secondary switchgear, typically rated up to maybe 630 amps and 12 kV. So some examples of solid dielectric switchgear covered by, in this case, we've got examples of -201, so that's what we call insulation enclosed. It does not necessarily, or it does not have a metal enclosure around the high voltage conducting parts. So the two examples on the left and in the middle are common in the US. Those are effectively load break switch ring main units. And each pole you can see there consists of a solid embedded pole, which has got an earth-screened layer on the outside. And those are covered by the American IEEE C37-74 standard. And have been used for many years. On the right, those of you who've ever been involved many years back with some of the Type A mini subs, that's a ring main unit, very much of the type covered by -201. So the category of insulation enclosed medium voltage switchgear assemblies, and that effectively has a fused tee-off and two ring switches. And there are examples of those still in the network today. Another few good examples of screened solid dielectric switchgear, where you can see the main poles and how the different functions are then interconnected with screened solid dielectric busbar systems. And these examples again are common in the US, and they're not metal enclosed switchgear assemblies. Here are some examples of solid dielectric switchgear under -200, which is metal enclosed, which would effectively be covered by SANS 1885. And you can see their typical metal enclosures as we would be familiar with, but fixed pattern, and you can see the epoxy resin insulation embedding all the primary conductors. What we see here are all examples of unscreened solid dielectric switchgear. And then you've got the fully screened type, which also of course falls under -200 with a metal enclosure, covered also by SANS 1885. And on the left is the Schneider Prem set, secondary, although the ratings are increasing now up to 1250 amp 25 kA, but fundamentally a 630 amp switching device. And then on the right is the Actom GelPag solid dielectric insulated switchgear solution, which we'll talk about in detail later on. So what are some of the general advantages of SAIEE? Firstly, there's no insulating fluid or gas, and therefore no associated monitoring or leakage to worry about. No SF6, so it certainly is a good alternative to SF6. And because of the dielectric properties of solid insulating materials with a high breakdown strength, high kV per millimeter, you can design switchgear that is relatively compact. Now, some of the disadvantage of unscreened solid dielectric insulated switchgear. Firstly, there's external insulation, which Johan will cover later in his slides, which is insulation which is exposed to atmospheric and environmental conditions. And therefore, you have to consider creepage as well as clearances as well as creepage distances. And effectively, because they're exposed to the environment, that They require periodic cleaning and therefore maintenance. It's not a maintenance-free solution. And that has pretty much been, I would say, the downfall of unscreened solid dielectric switchgear in the past. It relies on the combination of solid dielectric and air for full insulation. So we would actually say that's effectively a hybrid insulation technology, because the electric field is not restricted to just within the epoxy resin or alternative solid dielectric material. It's a combination of the resin plus the air. It's a bit analogous to talking about a covered conductor versus a fully insulated conductor, or a conductor with insulation applied around it versus a screen cable. And really, in our opinion, that would not really be true SIS or genuine SIS, because it is effectively a hybrid solution. So then, in terms of fully screened earth screens SIS, the benefit of that is that there is no exposed external insulation, effectively immune to the effects of pollution and moisture on the primary circuits. No maintenance is required. And on the primary circuit, we're not saying, we wouldn't claim that it's maintenance free, because as with other fixed pattern or GIS solutions, still inspections and checks are required on the operating mechanism. The big benefit is, along with pressurized GIS solutions, is that it's immune to altitude derating of the insulation levels. There's no exposed live parts, even after accessing a high voltage compartment, due to the earth screen layer on the surface of the switchgear. And the primary or the failure mode, if any, would be phase to earth, particularly in the case of where each individual phase is individually screened and earthed. And if, as in the case of South Africa, where the fault levels are limited by an NER, neutral earthing resistor, the risk of internal arc is effectively negligible. Then continuing, focusing more on some of the benefits of the Actom GelPag solid dielectric insulated switchgear solution. This is, we believe, leading the global market in terms of this technology, with a 30 to 40% space saving when compared to AIS and even some GIS solutions. What is really unique to this particular product is that you have visual confirmation of the isolating distance as well as earthing, and we'll look at that in a couple of slides. It incorporates proprietary bellows and seals, which are critical to ensure the isolation for the drive mechanism to the moving parts within the embedded pole, screened embedded pole. And then effectively through advanced nanomaterial technology, the thermal conductivity and dielectric performance has really been optimized to achieve higher ratings than have been able to achieve in the past. And we'll look at those as well during this webinar. What is also great about the modular design, the plug and play design of a solid dielectric solution, is that you can very easily accommodate front or rear cable access, top or bottom, as well as direct rear entry, which we're doing currently for an e-house in a particular application we're working on. The solid dielectric module, which is called the SAIEE module, has been tested underwater for 4 days, and then dielectric tested after that. Obviously, that would not include the operating mechanism. We're talking about the high voltage primary circuit. And that's effectively because all the dielectric stress is contained within the solid dielectric insulation, as Johan will talk about. This is just a side view, and we have included this presentation in the handout, so I won't go through every component, but just showing some of the key features, as well as the ability to have a visual confirmation of the isolating distance, which is something that you don't, or is often a problematic when it comes to fixed pattern switchgear, because you don't have the withdrawable circuit breaker and therefore a visual confirmation. And so this provides visual confirmation through a special viewing window and mirrors, and you can then confirm, in addition to the mimic diagram and position indicating devices, the actual status of the 3-position switch. And these slides just show those 3 positions. So effectively, looking at the top part of the I don't know if you can see my mouse, but the top section is the 3-position switch, sometimes referred to as the DES or disconnecting earthing switch, and the bottom section is the vacuum interrupter or the circuit breaker portion, and they are connected in series to form effectively the incomer or feeder, otherwise known as the branch circuit. So on the left-hand side, we've got the moving contact is in the closed position. It's driven by a spindle mechanism and a tubular moving contact. In the middle, it's in the open position, and then on the right-hand side figure, the moving contact is moved to the left, which is the earthing position, and the corresponding what you see through the operating windows is shown in the bottom. So just in terms of the architecture, as I said, this is beyond the scope really of this webinar to go into the details, but the IEC defines different types of access that can be given to accessible compartments. Obviously, by definition, it doesn't apply to a non-accessible compartment. And typically, if you access a non-accessible compartment, you destroy the integrity of that compartment. For example, the gas would be let out if it's GIS. So you have interlock controlled, accessible compartments, procedure-based as well as tool-based. And I think what's important to note is that, and it's often maybe missed, is that only interlock controlled and procedure-based compartments are allowed for normal use. A tool-based accessible compartment is only can be provided, but should not be. It's not intended to open a tool-based accessible compartment during normal use. And normal use is defined in IEC as well, and it's also ultimately up to the manufacturer to define what is normal use. So looking at a typical SIS or the JLPAG architecture, as you can see, it's a metal enclosure, as we would be familiar with different high voltage compartments. Although there's only one accessible compartment during normal use, and that is the cable connection compartment, and that is interlock controlled. The other compartments, which contain the switching device, which is compartment D, which is the 3-position disconnector and vacuum circuit breaker, effectively incorporated in the SAIEE module, is a tool-based accessible compartment. It's not required to access these compartments during normal use, as well as the bus bar compartment. It's only needed for installation or dismantling at the end of service. And then, of course, you've got the low voltage compartment. Something else that's covered, again, won't go into details of the different definitions, but loss of service continuity is an important classification that was introduced into the 62271 series of standards. And it's effectively a category defining the possibility to keep other high voltage compartments of a functional unit energized, as well as adjacent functional units when opening its connection compartment, which is the cable compartment, or any other of its high voltage compartments in normal use. So it only again applies to compartments that require access in normal use. So there's 4 definitions, and these will be in the notes, but I just want to focus in or home in on LSC 2 and to make a comment that in terms of fixed pattern switchgear, such as GIS or solid-dielectric insulated switchgear, SIS, there's effectively one category that's relevant and applicable, and that is LSC 2. And that's primarily, well, because the only accessible compartment is the cable connection compartment. You cannot actually get LSC 2A or 2B with fixed pattern switchgear, because the other compartments are not required to be accessed during normal use. So it's only limited to LSC 2. And that's effectively a category of functional units having at least a separate accessible compartment for the high voltage connection, that's the cable connection of that functional unit, such that when that compartment is open, at least one bus bar may remain energized and all the other functional units of the assembly may be operated normally. So that provides the maximum level of service continuity possible. Here's an example of the architecture of an LSC2 assembly. We've got two examples. The top example is an example that would be, which is similar to the GelPag SAIEE primary switchgear, where you have a separate bus bar compartment, a switching compartment, which includes the circuit breaker and disconnector, an earthing switch, and then the cable connection compartment. Obviously, in this case, the cable connection compartment is the only accessible compartment. Below that is a typical example of a ring main unit, where the bus bar is combined with the switching compartment into a single gas tank, or into a single compartment if it was solid dielectric. And what's important is that when accessing the accessible compartment, that the switchgear, the cable must be isolated and earthed, but the bus bar can remain energized, and other adjacent functional units of the same section can remain energized. Just briefly, before I hand over to Johan, just to talk about something which should really not be an issue and ultimately left up to the manufacturer, but is just the main circuit configuration. And this applies not only to solid insulated switchgear, but also other fixed pattern technologies. And I'm referring to the position of the 3-position switch relative to the circuit breaker. So in fixed pattern switchgear, you have the 3-position switch, which provides which includes the disconnector and earthing switch, and provides the isolation requirements necessary in terms of the standard, and then the circuit breaker for the making and breaking performance. So when the 3-position switch is located above, all the switching and making breaking capabilities fulfilled by the circuit breaker. The 3-position disconnector is simply a 3-position switch and has no making, and it does not require to have any making or breaking capabilities, and is therefore an economical solution, and effectively just provides the 3 different positions. Earthing of what's important to note is that earthing of the circuit breaker is done, earthing of the cable is done via the circuit breaker. In the example below, or underneath, we've got a reversal of the order where the circuit breaker is above the 3-position disconnector. In terms of fit, form, and function, these are equivalent, and but however, when you have the bottom configuration, now you can no longer rely on the circuit breaker to do all the making and breaking, because when you're closing the switch, the earthing switch is downstream of the circuit breaker, and therefore it's required to have a making capability, if it is of course rated E1 or E2 in accordance with 62271-102, which requires it to have a short circuit making capability. So then you need a special operating mechanism, typically a spring operating mechanism, to ensure that the speed of the earthing switch and the closing and the contacts are suitable for that making operation. So economically, it may not be as viable. And as I say, ultimately, this is something that should really be left to the manufacturer and not predetermined or specified by the user, because functionally, they are equivalent in terms of the user. Right, so I mentioned that what we've really seen is that the boundaries and the ratings of solid dielectric switchgear really being pushed. Just focusing in on the Actom GelPag switchgear, we've mentioned other examples here, but just looking at that, currently we have a 12 kV, 95 kV solution rated all the way up to 4,000 amps. And although we put the 4,000 amps in brackets because that requires forced cooling, it's effectively can operate at 3,150 amps without forced cooling. And that's quite significant because of the losses. The I²R losses is something which is always a challenge with solid dielectric switchgear, and Johan will touch on that in his portion of the presentation. But what's remarkable is that it's a 40 kiloamp short circuit rated, and the width of the panel up to 1250 would be 500 millimeters, 700 millimeters up to 2,500 amps, and then for the 4,000 or 3,150 it would be at 1 meter wide. which is a considerable space saving compared to other alternatives. And it's great and exciting just to point out that we're currently working on a 36 kV, 40.5 kV solution with our partner Gelpag for up to 2,500 amp and 31.5 kA, which will be available from the middle of next year. We're currently busy with the type testing of that solution. That would be 800 millimeters wide. But for the sake of time, I'm now going to hand over to Johan Jordan to take you through some of the more interesting technical parameters on performance.
Thank you, Red. Good morning, ladies and gentlemen. In order for us to understand and explain some of the technical details related to solid dielectric switchgear, we just need to review a few of the electrical principles that is applicable to the switchgear. In terms of electrical stress, when you've got voltage being applied between two electrodes, there's an electric field set up between those two electrodes, and the electric stress that is appearing in the gap between those two electrodes is effectively numerically equivalent to the voltage gradient across that material. So for where there's a high concentration of voltage in terms of the voltage gradient at electrodes, you will have a high stress concentration in that area. The dielectric strength of an insulating material is effectively the ability of the material to withstand the electric stress. So if you exceed the dielectric strength of the material by applying too much voltage across it, and you're exceeding the dielectric strength, a voltage breakdown in that material would occur. So the electric stress and the field is basically created, and what affects the electric field is the magnitude of the voltage that is being applied on these two electrodes, the distance that those two electrodes are apart from one another. The closer they are, the higher the electric field would be between them, and then also the medium that is placed in between those two electrodes. So if you have air compared to a solid dielectric, the stresses in those dielectrics would be different. And the physical shape of the electrode also then determines the amount of stress that is appearing on the electrodes. So sharp edges, small radiuses would typically have a higher stress concentration than even smooth surface or very gradually radius electrodes. So when an electric field is applied between two electrodes, the free electrons in the medium basically gets accelerated in a field. Those electrons gains kinetic energy, and that kinetic energy is enough when they collide with other molecules to knock another electron out from the molecule to create ionized molecules. So these electrons and free electrons that are now being released from the molecules then accelerates towards a positive electrode, and the ionized molecules that is now created, the positive ions, is then accelerating again towards the negative electrode. So when you increase the voltage between these two electrodes, more and more electrons is being released and accelerated in the gap, causing more and more collisions with other molecules, which eventually causes a voltage breakdown. And this is known as the Townsend avalanche effect, due to the high concentration of conductive and ionized medium in between the two electrodes. The voltage breakdown, or the voltage at which breakdown occurs, depends on the air density. So if you have got a low air density, for instance, at high altitudes, the spaces between the molecules is big enough for the electrons to gain enough kinetic energy so that you don't need a high voltage to drive to accelerate the electrons to create a breakdown. at high incident, high air densities at, for instance, low altitudes, the space between the molecules is very small. So, and then because of the denseness of the air, and you don't have enough space for the electrons to gain enough kinetic energy to release electrons. Another factor that determines or influences the voltage breakdown is the ionization of the medium. Some dielectric materials has got a stronger bond to the electrons in the electron structure. So you require a higher voltage to release those electrons from the dielectric medium. Another factor that influences the voltage breakdown is pressure and temperature, and the high voltage test standard for high voltage test techniques defines that standard and pressure for altitudes less than 1,000 meters above mean sea level. So when you apply your insulation, or you review the insulation at altitudes above that, you need to have then certain correction factors that you need to apply to the applied voltage or the test voltage that you use. You either need to reduce the test voltage, or you need to actually increase your insulation that you require at higher altitudes. Now, the breakdown phenomena can be explained by an example that we can look at. And this is a typical rod plane scenario where you've got a electrode in the form of a rod, and an electrode in the form of a plane. Voltage is being applied between the two electrodes, which then gives a voltage distribution which is in the forms of the equipotential lines. Where there's a high concentration or a gradient in the voltage, you get then your electric stresses appearing is higher in those areas where the gradient is high. So when the voltage increases, the electric stress increases, and then partial discharge is formed. And if the voltage is increased to such a point where the electric stress in the gap between the rod and the plane exceeds the breakdown voltage of the medium in between, voltage discharge is actually formed. Now I've got a video that I can quickly show the phenomena in terms of the voltage breakdown. So the setup is that we've got the rod at the top and the plane at the bottom, and when the voltage is applied, you've got then the discharge happening on the actual electrode. As the voltage gets increased, more corona will form, more partial discharge will form, up to the point where the voltage, the medium between the electrode cannot withstand it anymore, and a physical breakdown will happen. So that's effectively the mechanism for having breakdown due to the high field stress. One of the German physicists, Friedrich Pascher, needed some studies of different gases at different pressures and the variation of the gap between parallel plates. And what he found is that at high pressure, for a fixed gap, at higher pressure, you need to apply a high voltage in order for the breakdown to happen across the gap. As the pressure is reduced, the breakdown voltage is also reduced, which then is the same mechanism as what I explained in terms of the Townsend. So at higher pressure, typically low altitude, you'll need a high voltage, and at a high altitude, at a lower pressure, you'll have a lower breakdown voltage. But what he found is, as we approach the vacuum pressures, that the availability of molecules to release electrons in the vacuum becomes less, and therefore the breakdown voltage also then increased. And that is why vacuum, in terms of vacuum interrupter, is such an ideal dielectric medium to interrupt and break current in a vacuum with very small compact distances. The other conclusion that he made, at constant pressure, you require higher voltage to break down for larger gaps. And as I mentioned before, the bigger the spacing between your electrodes, the higher voltage you require to break down the gap. Now, relative permittivity is one of the important parameters, material parameters, that is used in the evaluation of electric fields when one does the field plot simulations. The dielectric relative permittivity is basically a property of the material that indicates the degree of polarization of the material in the presence of electric field. And it's relative to the absolute value that is epsilon 0 in vacuum. So for epoxy resins, you've got, for instance, 3.5 is the value for polyurethane epoxy compared to vacuum, which is 1 in terms of relative permittivity. In terms of air, it is just above 1. So for all practical purpose, in terms of standard temperatures and pressures, it is taken as 1 when we do field plot simulations. So the effect of relative permittivity is that the high permittivity materials tends to shift your electric field stress into the low permittivity materials. So if you've got epoxy and air next to one another, the epoxy with a higher permittivity would shift the electric field into the air. And then that is what we will see when we look at partial discharge forming inside voids when we look at the electric material. So partial discharge, as I've shown in the video, can happen when there's a high field intensity on the electrode surface in air, but we also get partial discharge in voids inside the electric material, shown by the following example. So in this example, we've got 2 parallel plates energized at a voltage with the electric material in between. So because of the 2 parallel plates, we have a uniform field distribution between the 2 plates. In this case, we've got a relative permittivity material of, say, 2.2. And if we introduce a void inside the electric material, the field intensity is then moved into the area where there's a low permittivity. Although it is basically a 2-to-1 ratio, the field concentration is then moved into the field, the void. So if the voltage between these 2 parallel plates increases, the stress inside that void will also then increase up to the point where the breakdown strength of air is then exceeded, and then partial discharge will form inside the void. One effect of the partial discharge is that you also then get material erosion, and then over time the material will degrade, and you will then eventually get a flash over between the 2 electrodes. This is even true for a void that is trapped on the surface of the electrode. Sorry. Moving then on to external insulation and creepage. The insulation material is used in form of post insulators or support insulators to fix live conductors or support live conductors in a geometrical position between live and ground. IC 62271-100 defines the external insulation which then includes distance in atmospheric air, in other words, clearances between phases or between insulation or electrodes, as well as the distance along the surface in contact with atmospheric air. In other words, creepage across the surface. Now, creepage is defined as the shortest distance from the live end to the earth end of the conductor over the surface of the insulation. And we sometimes refer it to as the lazy end, walking across the insulation, having the shortest distance. So that is defined as the creepage distance across the surface of the insulation. Now, because you've got a potential difference across the insulation, there would be, and you've got a surface resistance or conductivity on the surface, there would be a leakage current flowing over the surface. In terms of the insulation itself, when it's clean and dry, you've got a very low surface conductivity. So the leakage current over the surface would be very, very low. So when dust particles and moisture gets in contact with the surface, which then dissolve the dust and the salts inside the dust, then the conductivity of the surface increases, and the leakage current on the surface then increases. By adding additional sheds on the surface, as shown there in the image here, you're basically increasing the surface area of the surface, you're increasing the creepage distance, and the leakage current path you're increasing, effectively lowering the leakage current that will flow over the surface. Now, the specific creepage is then defined as the creepage distance divided by the rated voltage, and then in terms of SANS 1885, which then requires a preferred specific creepage distance of 20 millimeters per kV, which means then the actual creepage distance for 12 kV system should be 240 millimeters, and then for 24 kV 480 millimeters when you measure it. Now, the effect of high creepage current over the surface is formed into results in two possible defects or degradation of the material. The first one is tracking, which is basically conductive paths that is developing on the surface of the insulation, and even under dry conditions, those tracking paths remains conductive. Erosion is basically a non-reversible degradation of the material, where material is effectively eroded, and the molecules of the material structure is eroded, and you actually have material loss, creating then this material surface defects. When we look at what drives erosion and tracking, is the probability of tracking and erosion increases with the increase of leakage current. So you need to keep your surface clean on the insulation in order to reduce the leakage current, in order to reduce the probability of tracking and erosion to happen. When the leakage current decreases, especially in polluted environments, the leakage currents would actually generate heat on the surface, causing dry bands to form. When you get the dry band form, a voltage drop develops across this dry band, which will then result in arcing across the surface. This arcing across the surface, basically due to the temperature of this arc, will have an effect on the material, and depending on the material type and the material composition, it will either then erode, or it would cause then carbonized tracks to form on the surface of the insulation. These are just some examples of a type C bushing where the cable termination was not properly done, where we actually have a tracking and a tracking and erosion happening. So both phenomena is possible if the cable terminations is not properly done. Now, in terms of air-insulated circuit breakers, the vacuum interrupters is exposed to normal atmosphere, And in a closed, when the vacuum interrupter contacts are closed, the insulation surface or the external insulation is effectively short circuited by the contact. So there's no leakage current flowing over the surface. But once the vacuum interrupter opens up, you effectively have the external creepage on the outside of the vacuum interrupter that now need to deal with the effect of pollution. So because your vacuum interrupter is directly exposed to the atmosphere, you need to make sure that it's got enough creepage over the surface in order to make sure that it deals with the effect of leakage current. In terms of a bedded vacuum interrupter, when you now embed the vacuum interrupter into an epoxy resin, you still got external leakage or external creepage surface from a earth potential to the live potential. And you need to make sure that the creepage distance over that external surface is still sufficient in order to make sure that the leakage current is then controlled. In terms of an embedded vacuum interrupter in a screened epoxy surface, your earth screen extends up to the point where typically your cable terminations and bushings are done. So your exposed external creepage extends basically from the end of your earth shield. But now you may say, but this distance may be shorter than what you would have normally with normal embedded epoxy. But in terms of screened SAIEE switchgear, all the connections to the high voltage components like bus bars, cable connections is done through screen separable connectors, which basically forms an earth layer on the outside exposed to the atmosphere, where the inside surface is then basically sealed off from the atmosphere, and it is then controlled by the interface fit between the screen separable connector and the actual switchgear module. To further illustrate the effect of the earth screen, I've got an example that I've done with a few field plots where we looked at a bus bar setup supported through insulators on basically through wall bushing on a metal plate, and to evaluate the field plot and the effect and the field of the voltage with the bus bars screened and the insulator screened and without the earth screen applied. So if we took a slice through the setup, we get a 2D view of the bus bar setup, where we've got the 3 phases, the conductor running through the earth plate, which is in this location is the earth plate, and then insulators supporting the bus bars. The voltage being applied at any moment of time is effectively the 3-phase system, where we've got the yellow phase, for instance, on the peak, and the red and the blue phase would be then as a negative voltage relative to the earth potential. This plot shows the field plots without the earth screen being applied, and the important thing to note on this is that you've got a voltage distribution between the phases, and you've got a voltage distribution and a voltage gradient from the live end up to where the earth potential is. So with a potential difference, and you've got pollution on the surface of the insulation, you will have then leakage current flowing over the insulation surface. You've also got high field concentration at the interface between where the bushing goes through the metal sheet, which if you're not having a proper insulation material, or the bushing is not properly dimensioned in terms of the dielectric strength, would cause then a breakdown in that zone. If we now apply an earth screen on those bus bars and insulators, we effectively get this field plot. And the outer surface is basically where the earth potential is sitting, and what can be seen is that there is no voltage distribution on the outside of your earth screen. There is also no electric field on the outside of the earth screen, and the field is contained within the epoxy between the main conductor and the earth screen. So therefore there is no voltage on the outside of the earth screen that would drive any leakage current across the surface of the earth screen. Looking at the two scenarios just from a field plot and the field in the air, as I mentioned before, your high permittivity material tend to push the field into, to shift the field into the low permittivity material. So in this case, we do not have an earth screen. The field stress inside the epoxy is low, but then the field inside the air is high. Compared to where you've got an earth screen, the field inside the epoxy might be 3 times higher, but in the air there's no field, or the air is not being stressed. And the design of the electrode and the design of the epoxy around the electrode is controlled and can be done properly, so that you then you can control the magnitude of the appearing field stress, that you don't exceed the dielectric breakdown strength of the epoxy. One of the other components, and Narek touched on this in terms of the thermal conductivity of the epoxy. Not only does it need to deal with the electrical stress, you also need to deal with the thermal stress of the material. During normal currents, the higher the currents, the more heat is being generated, and the epoxy need to be able to get rid of that heat in order to still maintain the rated current. Heat transfer can be done as a combination of 3 methods. The first one is radiation, where the heat energy transfer is done by emission. Convection, where airflow or fluid flow in motion is basically getting rid of the heat energy. But in case of solid dielectrics, conduction is a dominant means of energy transfer in getting the heat from the conductors. By adding additional fillers into the epoxy resin, your thermal conductivity can be changed, and you can actually get up to 10 times the thermal conductivity of your resin by adding these fillers. But by adding the fillers, by adding the specific type of fillers, you're changing the electrical properties of the epoxy as well, to be either more insulative or more conductive. So by selecting the correct fillers, you actually need to create a more insulative epoxy with high thermal conductivity rather than a conductive epoxy. And that's nothing to do with the earth screen layer on the outside. This is the body of the epoxy between the conductors and the earth screen. And with polymeric research that's currently being done today on resin and epoxy resin with nanotechnologies, the thermal conductivity increase is achieved, where we can get up to 3,150 and even 4,000 amp current ratings on solid dielectric. In summary, with the unscreened switchgear, typically AIS, and even unscreened epoxy insulation, the electrostatic field is pushed into the air and stressing the volume of the air. The air is uncontrolled in the medium with respect to moisture, electrical pollution, and foreign particles. Where screened epoxy insulation, the electrostatic field is contained within the epoxy, and by selecting your epoxy material properties and your electrode design on the inside of that epoxy, you can actually control the electrostatic field appearing not to exceed the permissible breakdown strength of the epoxy. No electric field nor potential exists outside the earth screen that could drive leakage current that could lead to cracking or erosion of the dielectric material. And with solid dielectric material with an earth screen layer, it's therefore immune to degradation effect of or derating effect of altitude, moisture, and pollution. And with the application of advanced polymeric materials, we can achieve current ratings of up to 3,150 amps and 4,000 amps with additional forced cooling. Thank you. That is all from our side.
Thank you, Johan. Just back over to me to wrap up. I think for those of you who read the webinar, it was actually in the form of a question. It said, is effectively asking the question, is solid dielectric insulated switchgear the future of MV? Well, certainly fixed pattern switchgear. There's a question mark in there, not necessarily saying that it is the only option going forward, but it's certainly an option that's becoming viable. And in terms of the developments and technologies, and as Johan has described, something that we see coming back to the fore and perhaps taking a bigger role than it has in the past. The other aspect we mentioned was, and hopefully some of the issues have become clear, was what to be aware of if you are going to consider purchasing solid dielectric switchgear or even specifying it. So first of all, it's covered by the standards effectively. There's we've talked about all the concepts applicable to -200, and all those same principles and concepts apply to solid dielectric insulated switchgear, which is housed within a metal enclosed assembly. So the reference standards are the same, -200, IEC 62271-200, which has been adopted as a SAN standard without any deviations. And then the front end SANS 1885, which was previously NRS 003, which provides preferred requirements for users within South Africa, noting specific South African conditions and industry norms. So they still incorporate mechanical switching devices, and the classes of which would be the same when it comes to AIS, GIS. So your mechanical endurance, your electrical endurance, the capacitive switching performance, the application class S1, S2, all of those remain the same, nothing special in that regard. And so it's just important to bear that in mind. Loss of service continuity, because it's fixed pattern, it's important to bear in mind that only LSC2 is effectively applicable. And that's because you have one accessible high voltage compartment, and that's the highest level that is available for a fixed pattern architecture. So although SIS does not make use of moving shutters, you still have partitions between the compartments, and it would be our recommendation, and in fact it's specified in SANS 1885 that those are metallic. Although in theory then it's of no real concern, because the high voltage circuits contained within the different compartments are effectively touch safe by virtue of the earth screened layer on the surface of the solid dielectric insulation. So that effectively, I think what we would certainly stress is that for solid dielectric insulated switchgear, or to derive all the benefits from it, it's really essential that the switchgear is fully screened. And in other words, that all the insulation is covered with an outer earth screen layer. And I hope that's become clear through Johan's detailed explanation of the different phenomena, creepage, clearances, and so on, because once you then screen it, you're eliminating leakage currents as well as the need for clearances between poles and phases. So it's important to also bear in mind, in terms of continuity of philosophy, that the cable terminations should also be screen separate, or should be done using screen separable connectors. Those are well defined in the SANS standards. So the accessories are covered by SANS 1332. That was previously NRS 053. That's been adopted as a standard, so that the requirements for the cable terminations are covered in that standard 1332. But it is also specified, those standards are specified through SANS 1885 and SANS 876. SANS 876, which is the insulation requirements for conductors and medium voltage enclosures, as well as requirements for cable terminations, defines 5 different types of cable terminations. Type 1 being a bare uninsulated termination, type 2 a shrouded or covered termination, type 3 is an unscreened separable connector, and then you've got type 4, which is type 4 is as a screen separable connector with an outer cone type bushing. Currently, the more common variation of a screen separable connector in South Africa, but it's also important to note that type 5 terminations are covered in SANS 876, and that is the inner cone or plug-in termination. Particularly, for example, at some of the higher voltages at 36 kV and where higher currents are involved. While the flexibility is provided by a type 4 outer cone separable screen connector or screen separable connector is very convenient in terms of being able to plug cables back to back onto one another to accommodate multiple cables per phase. One has to be very sure that you provide proper cable support because of the mechanical strain that could be placed on the outer cone bushing. So termination of cables and compliance with the requirements of SANS 876 in terms of support for the cable is essential. But with a type 5, although you need an individual inner cone bushing for each cable, that can be accommodated with the switchgear, and each cable is individually then mechanically supported when connected into the inner cone bushing. So we recommend both types, and to certain, and as I say, those are covered by the SANS standards. Then cable compartment dimensions. So dimensions required to accommodate, for example, 3-core cables, which are commonly used in South Africa, certainly at 11 and 22 kV. It's important again to ensure compliance with SANS 876, which, for example, specifies for a 3-core cable that you need to provide 800 millimeters from the cable support clamp or the gland plate, whichever is higher, and the terminal fixing point on the bushings or the copper tags, depending on the type of connection you're making. So when it comes to single core cables, like for example, which are used in the 33 or 30, we're using 36 kV switchgear. The SANS 876 has been amended to accommodate applications where it is known that single core cables will be used, and those dimensions have been reduced. And then lastly, some thoughts. Johan has shown us videos and described in detail the partial discharge phenomena. So while by virtue of the earth screen layer, you have the concern over surface discharge, in other words, the dry band arcing associated with leakage currents along the surface of an insulator are eliminated, as well as then corona, because there's no exposed insulation. There is the possibility of voids within the solid dielectric, and that comes down then to the quality of the manufacturing and the routine testing of the switchgear. And it's maybe worth noting that in 62271-200, where it covers PD testing, values for PD have not been prescribed, mainly due to the complexity and the fact that different switchgear assemblies incorporate different technologies ranging from gas to oil to air to solid dielectric. So it's very difficult to prescribe values. It is recommended, and it's in a note that for solid dielectric switchgear that PD less than 20 picocoulombs would be appropriate, which we agree with. In our case, we're even more conservative, and we ensure that the switchgear is complies with a maximum of 10 picocoulomb, so less than or equal to 10 picocoulombs. Right, so we mentioned we would touch on the EU regulations, obviously not applicable to us directly in South Africa, but it's worth mentioning that this year in February, the latest regulations were published and some defined dates have been published within the regulation. And as far as medium voltage equipment is concerned, from 1st of January 2026, no switchgear rated up to 24 kV can use fluorinated gases. And then from 2030 onwards, all other medium voltage switchgear, so up to 52 kV. And there's similar dates for switchgear rated above 52 kV. So while we, as I say, we're not covered by this, many of the switchgear OEMs are based in the EU and are therefore working on solutions, and it will effectively have an impact on the rest of the world. The Chinese are very aggressive in terms of developing non-SF6 switchgear solutions, including from a ringman unit level up to primary switchgear as well, and as well as in the US. So it will filter down through the rest of the world ultimately. And then in conclusion, so is or SAIEE solid insulated switchgear the future? Well, it may not be the only technology available for fixed pattern MV switchgear, but it's certainly a promising and viable technology with many, many significant advantages, as I hope have become clear through this webinar. It has the same performance aspects or immunity with regards to altitude and environmental effects compared to GIS. GIS is achieved by virtue of the hermetically sealed gas compartment and pressurized gas compartment, but it has the benefit of not having any greenhouse warming potential, global warming potential, GWP, as would be associated with SF6 and even some of the alternative gases, which, although they are much lower than SF6. And we do believe that it's important that when purchasing or specifying, that you are aware of some of the issues that have been raised, and that it's important to correctly specify and ultimately evaluate the switchgear. Thank you very much. Just some examples, some photos. This is a project we did recently for a BESS project, privately owned battery energy storage system. We effectively used the gel pack switchgear to create an outdoor outdoor enclosure, providing a switching station for that BESS project. And these are some installations of the gel pack at the Kamoa copper mine in the DRC, which is underground with extremely harsh conditions, very, very high moisture levels and humidity, and so really ideally suited for those environments. And that's it from us. Thank you very much. We really appreciate the time, and I think it's over to Minx for some questions.
Yes, thank you very much, gentlemen, for this very informative presentation. Ladies and gentlemen, before we get into the questions, please type your questions into the questions box, which we'll get to now. We don't want to run over time. I know you're all busy. We've got our first question here from John Wilson. How is the dielectric stress managed in the associated instrument transformers?
Okay, so in the same way. So let's talk about the current transformers. So the CTs are effectively low voltage toroidal type CTs, very similar to what you would have in GIS fixed pattern gear, and they are installed around or outside of the screened screen layer of the branch C. You can actually share our webcam for the questions. So yeah, they are located around the branch. So where the cable terminates, there's a section, for example, between on the branch tee-off where the CTs are located. If you look in the handouts, you'll be able to see the location of the CTs. So those are outside of any high voltage electric field stress area, and therefore effectively are low voltage CTs, and therefore not part of the directly connected to the primary high voltage circuit. In terms of the voltage,
the cable VT is also a screened epoxy resin screen VT, which is then connected to the rest of the module through a screen cable and separable connectors.
Thank you, gentlemen. And before we get into the next question, ladies and gentlemen, just be in the handout sections, you will find a copy of the presentation as well as some marketing information about Actom MV switchgear. Our next question is again from Mr. John Wilson. He's asking, are any bespoke lower power CTs and VTs available to implement digital sub technology?
Yes, so that's something we've been looking at. It's good because quite a few of our customers and users have shown interest in that. So, for example, on the units and due to the design of the solid dielectric switchgear, it becomes really quite a simple matter to plug in a low power voltage transformer in a similar way that you would plug. You have the option always of plugging it into the screen separable connector as a replacement for the back insulating plug on the screen separable connector. But we could also incorporate that on, for example, the tee-off. There's a tee-off bushing, inner cone bushing that we use to connect the conventional VTs, as Johan described, through a screened inner cone connector, and those then could be just simply plugged into those and used as an alternative. When it comes to the CTs, it's not really that critical. Because again, we're already using low voltage CTs which are outside and not galvanically connected to the main circuit. But however, the same could apply with Rogowski coils as well. But what we're still seeing is that the challenge is not so much on incorporating it in the switchgear. It's then using appropriately meters and protection relays that can accommodate the output signals from that, with or without a signal conditioning or conversion box. So, and then of course the accuracy of the equipment. The VTs currently really what's being offered is still class 0.5 at best.
Thank you, gentlemen. Our last question is from Mr. Bernard Meyer. He's saying, what impact of thermal cycling for renewable energy applications? I mean, what is the impact of thermal cycling for renewable energy applications on solid dielectric material?
Okay, so great question, Bernard. Nice to see you on the webinar. So, I mean, Johan can add, but effectively, one of the statements I made earlier was that solid dielectric insulation per se is not something new. We've had conductors passing through resin insulated CTs, block type DIN CTs, embedded pole technology. So the concept of the expansion and contraction of the conductors relative to the insulation is not something new. However, with newly formulated materials, it's always important to assess all these different issues, and a lot of accelerated testing has been done in conjunction with universities to verify the long-term performance of cyclic loading and expansion and contraction of the conductors under cyclic loading.
Yeah, I mean, some of the vacuum interrupters is actually encapsulated in a silicon liquid silicon layer that could act almost as a cushion for the differential expansion contraction between the epoxy and the vacuum interrupter itself.
Excellent. I did say we had a last question, but here's the last question from Mr. JD Voigt from Plantech, asking, the example of the gel pack gear in outdoor enclosure for the battery project, is this an example of a possible on-site replacement for secondary RMU solutions with primary switchgear solution? Drop-in replacement, is asking.
Yeah, in a way it could be. So yeah, it looks like a ring main unit on steroids because it's effectively 40 kA, 1250 amp, and then 1250 amp functional units. But in this application, it wasn't that. But effectively, yes, if the ratings of the particular application or the requirements exceed those typically associated with secondary switchgear, being 20 kA short circuit level and 630 amps, then yeah, it's been great because we've then been able to offer the gel pag as an alternative in an outdoor enclosure, as you saw there. So yeah, maybe best, as I say, call it a ring main unit on steroids.
Okay,
I don't hope that answered your question.
So okay, here's another question from Imran Mullah. He's asking, just to clarify, will screened SIS assemblies fall under S2271-200 and not 201?
Yeah, so they would fall under -200 if they are enclosed in a metal enclosure. They could theoretically fall under 201, but then 201 does not require any metal enclosure around the switchgear. So there were some photos earlier in the initial examples of, and that was an American application where you had fully insulated screened that would, if it was IEC, it would be covered by 201 because there's no metal enclosure, defined compartments that are on, or the assembly is not enclosed in a metal enclosure, and therefore they, accessible to, they're accessible. So it could be both, but in our case, it's most certainly -200, and we do not offer switchgear that complies to -201. So it's fully compliant with -200. And just on that, it just reminds me of an interesting debate that was held about 10 years ago with the IEC. Johan and I we're fortunate enough to be very involved through IMASA, the Electrical Manufacturers Association of South Africa, in IEC standards and the technical committees. But about 10 years ago, they just had a discussion because, I don't know if you're familiar, you've got GIS solutions that have screened bus bars on top of the switchgear, so that the panel's functional units are interconnected with external screen separable connectors. And many of the OEMs were saying, we don't need to put that into a metal enclosure, and because it's touch safe. It's got an earth screened layer on the outside. It's a fully screened bus bar system. Why do we need to put an enclosure around it? And this big debate then arose, and questionnaires were sent out as to whether or not a metal enclosure should be put around those bus bars. And it simply came down to the fact that if you want to claim, or if the switchgear is in accordance with -200, of which the title is metal enclosed switchgear, and there's no exclusion for which compartments don't have to be enclosed, then you need to have a metal enclosure. Obviously, the IP rating can be debated. It could be a mesh enclosure, but effectively it does need a metal enclosure around it to comply with -200. If it didn't, it would then effectively not comply with 200 and it would fall under 201. So yeah, just an interesting fact on that.
Excellent. Thank you, gentlemen. We've come to the end of the webinar. Before you go, please, I'm going to activate a poll for you on screen to please just quickly answer those. How did you learn about this webinar? This is just to make sure that we've reached the right responses and get the right attendees online. Not saying that you guys are wrong, but we would like to see more attendance. It is highly appreciated. And while we wait before we end, to please just click on the handout section and download the PDF presentation as well as the MV switchgear information, and then get into contact. On this note, I would like to thank everybody for your attendance. It's highly appreciated. Rhett and Johan, thank you so much for your time. It's very informative. And ladies and gentlemen, if you have any questions, please get in touch with Rhett or Johan. The information is on the presentation. Alternatively, you can just email me, Minx, M-I-N-X, @saiee.org.za. I thank you very much for your time today, everybody. Have a good day. Until next time, goodbye.